I think like this. Can the people online hear me? I think so.
Yes, we can hear you.
Okay. Okay, so I will start my presentation. The title of our paper is Can LLMs Leverage Observational Data Toward Fully Data-Driven Causal Discovery with Large Language Models. And my name is Yuni Susanti. I'm from Fujitsu, Japan. And this is a joint work with Michael Ferber from TU Dresden, Germany. He's also sitting on over there. Okay. Okay, so one of the fundamental tasks in various disciplines of science is to find the underlying causal relation and make use of them. So, for example, the causal relation would be like whether smoking causes lung cancer and whether taking an aspirin would cause an insomnia. So, this kind of causal relationship. And so that conventionally, the causal discovery estimate causal structure from observational data and generate the causal graph as a result. And this is using a statistical-based approach and called statistical-based causal discovery. So for example, suppose we have an observational data like this on the right side. And then with the statistical-based causal discovery, we will have the output on the left. This is called the causal graph. And then the causal discovery in the era of LLMs, there is this new concept called knowledge-based causal discovery. And basically what it means is LLM-based causal discovery. So instead of using an observational data, focus on the metadata, so more like the names of the variables or the textual description of those variables. And then, so rather than the actual data values of the observational data. And one of the other purposes of this knowledge-based causal discovery is to verify the causal graph from statistical-based method. So this is the causal graph from the statistical causal discovery method. And then for every pair, we ask the LLM whether the causal relationship is correct or not, basically this knowledge-based causal discovery. So one of the limitations is then it will, this method will depend a lot on the quality of the metadata, the textual description of whether, and the specificity, so how we describe our variable and our metadata to the LLM itself. And the other thing is also we fully reliance on the internal knowledge of the LLMs, make it prone to inconsistency and the hallucination of the other LLMs issues. So but even so, the progress in LLM, its advances in reasoning, especially in the text-based inference. So one of the question is, so can LLMs actually directly process observational data for the purpose of this causal discovery? So to inferring the causal relationship between pair using the actual data value. So can it handle those actual data instead of only the metadata? And so one of the challenges is how to basically, because LLM is prompt-based, so how to prompt those observational data for an effective LLM processing. And we've said like observational data. So what is actually an observational data? The key points here is it is a data collected by simply observing existing conditions. So there is no control experiment or intervention manipulating any variables. And for example, in the study of whether smoking causes heart diseases, so an example of observational data would be like a medical record, patient health record, for example, the patient age, gender, their smoking status, whether they smoke or not, and also their condition of the heart disease, whether they have, what is the condition of their heart disease. And yeah, for the other study, like whether a higher education spending causing lower employment, one of the example of observational data could be the data set from the World Bank, like the GDP of certain country, the employment rate, and this kind of example of observational data. So in the related works for this knowledge LLM-based causal discovery, there are several combination, and this is I summarize a bit. So one method is basically just direct prompting of the metadata. So just basically asking LLM whether there is a causal relationship between two variables with this and which one causing which one, something like that. The other is combining the prompt base together with a full with a supervised approach. And like on this here, the related works on the second, it's combining the prompting and supervised approach, prompt-based learning. And then the last is also some studies combined with the statistical-based causal discovery. In this case, the LLM is often used to extract the prior knowledge or like prior knowledge that will be used for the statistical-based causal discovery, or using the LLM as a feedback agent, those kind of combination. So this is the related works. However, as far as to our knowledge, there are no research yet that directly uses the observational data and asks LLM to basically somehow infer causal relationship from those data. There is one quite similar work here, but instead of using the actual data values, this work on the number 5 there, it calculates the statistic like a correlation between the variables in the observational data and give those statistics to LLM. So those are exist. So here we formulate the task formulation given a set of variables in the causal graph. So the objective is to infer the causal graph between all of this variable. And here the task is formulated as a classification task. Basically, we ask each pair of variable must be classified into those three. First is whether the first variable causing the second variable, or whether the second variable causing the first variable, and last is there is no causal relationship. So yeah. So here our approach extend the existing KBCD knowledge-based causal discovery by integrating observational data directly into the prompt. So yeah, like for example, our so we need to prompt this observational data and immediately ask the LLM through the prompting. However, the observational data usually is quite large, and because of the limitation of the length of the prompt length, we apply some sampling function to extract some representative subset of the observational data to fit into the prompt. And we tried several common widely used sampling function here with a case size of the data, how much data we want to include in the prompt. And then this is about our real prompt structure. So the causal discovery is conducted using LLM by formulating structured prompts. Here our prompts will contain the V here is the variables. So basically the variables. K is any prior knowledge or basically any additional information that can help the LLM in a way. And the last is the observational data. And for the prompting strategy, there are a lot of new prompting strategy. Here we compare this quite common one, and that's quite recent. The first is the pairwise prompting, and the second is the BFS breadth first search prompting that is inspired by the BFS graph traversal method. We will explain for each prompting one by one. The first is pairwise prompting with observational data. So here, basically, we ask the LLM about the causal relationship between individual variable pairs. So given a variable pair, the LLM is instructed to determine whether causal relationship exists considering the given observational data. So here we are asking two, basically, the existence. So whether one variable is causing the other variable, and second is also if a causal relationship does exist, is it the first causing the second or second causing the first? And this is the real example of our prompt that we use. Here you can see on the task part is the instruction basically to the LLM. Oh, sorry. And here the blue, here is the observational data. Of course, this is only an example, but yeah, as many, And then here we give LLM the choices. So LLM should answer choosing the choices, whether, the first variable causing the other, or just basically one of the three category that LLM should answer. And then the second prompting method is BFS prompting with observation here. So one of the merit of pairwise prompting is because you have to make all of the combination of all of the pairs, so it could be impractical when you have very large graph. So this BFS is inspired by the breadth versus traverse graph traversal, and so you will have less combination using this method. And so this is the real example of the prompt that we use in this prompting strategy. It's composed of several steps. The first one is called initialization step. Here you first identify all of the variables that are not causally influenced by the other variables in the graph. And then the second and also the third is the expansion. Here you identify the set of variables that causally influence by the current nodes, and you do it iteratively while inserting to the final causal graph. There is some certain strict condition. For example, if it is a loop, so you don't include that in the final causal graph. This kind of yeah. So yeah, this is the blue part is where we include our observational data, and then different to the pairwise, here we don't give the option, and because we need the variables here. So we ask the LLM to directly respond with the name of the variables. We constrain the LLM output into the name of the variables. So this is our experiment setting. We use this version of GPT-4 checkpoint. We conducted the experiment using the LLM for all of the experiment 4 times with the variation of the changing the temperature, and then we average the scores basically. And yeah, for the sampling strategy, we use the widely used sampling strategy. And for the number of the observational data included, for LLM based, because we have the limitation in the prompt length, we only include 100 observational data this time. And for the statistical-based causal discovery, we experiment with 3 size. The first is using 100, and then medium like 500, and then 1,000 observational data for more fair comparison. We use these 3 benchmark dataset from the Bayesian network following the previous works. Our data is 2 in the biomedical domain, and 1 is in the more the general, and this is like a survey on the social study. And this is our result. We use the metrics of the classification task, precision recall of measure, and also this Hamming distance and ratio following the previous works. And then so here we will discuss the result based on these 3 research questions. First is the impact of including the observational data, whether it improves the accuracy of the causal inference. And second is how does it compare to the conventional statistical-based causal discovery. And then the last is we experiment with 2 prompting strategy, and now which one is actually perform better in our data in our case. So the first finding is so incorporating the observational data does improve the performance, and it consistent across the both prompting strategy. So here, so you can see that it consistently improve. And on the pink part, the best performing model overall is also using the observational data, especially this BFS prompting. And And then the second finding is LLM-based method is improving over the statistical causal discovery method, and we get the consistent F-score improvement ranging from across all data sets. However, we also found out that the performance of the statistical-based causal discovery depends on the sample size. So as we can see here, when we use more data in the statistical-based causal discovery, we have less improvement, which just makes sense because more data normally. So to say that the LLM-based method will be more useful if, for example, you only have like limited number of data that you can use. So in that case, the LLM could be more effective. And then our third finding is that the BFS prompting method consistently outperform the pairwise prompting. And here, as we can see here, the pink part is the highest across all of the data set, basically the highest performance, and it is using this BFS prompting method with observational data. And we also observed the highest up to 0.32 points difference. However, in the BFS prompting method, it also included the entire chat history, which could lead to excessive prompt length. So that's also one thing to think about. So yeah, as for the conclusion, we investigate the potential of LLM for causal reasoning over observational data, and at least in our data set, in our current experiment, it outperformed the statistical causal discovery baseline, and also the improve over the LLM without observational data. So yeah, and our work demonstrate the potential of this combination of neurosymbolic in causal discovery, especially using this causal graph structure plus neural method, which is LLM. Yeah, and then as for the future works, we wanted to, especially the most important is how to handle this prompt length and how to choose the best, basically how to sample the observational data. In our current experiment, we don't find a lot of difference actually using several sampling methods, but maybe there are more advanced sampling methods that can give better improvement. So, yeah, thank you. That is our talk. So I would be happy if there's any question.
We go back to, first of all, thank you a lot for the talk. Really nice.
Okay, thank
Can
you.
we go back to slide 16?
16. Okay.
The results. So did you also compare your approach with other algorithms? Because you just use Pearson correlation.
Yeah, actually, for the statistical, we use only these two. Yeah. Yep. When we actually take.
And the second question, but I think it would be interesting to look into more
recent
advanced.
Yeah, exactly. Yes.
Pearson correlation. And the other question was, you used 3 different data sets.
Yes.
And you used at the same time different sizes of observational data.
Yeah, we wanted
Did you also try it, like, for example, use the survey data set just with 100?
Yeah, we did, but we did not include all of the results actually. Okay. Yeah.
And how was that, for example, just out of interest? How would survey data set work with n equals 100?
So I think, for example, in this, when we use the survey using the 1,000, we observe like smaller improvement, but it doesn't happen to all the data actually. I forgot which one, Asia or Cancer, but there are also cases even when we use higher, the more number of the sample, the difference does not really change, for example. So there is no, at least in our current experiment, there are no certain pattern.
Okay.
But at least, in this certain example, we did observe that the more data we use, we get smaller improvement, but it does not happen to all of the data.
And what's your intuition of that?
I mean, naturally, because the statistical causal discovery depends on the data, so I would think that more data would lead to better result. But maybe, for example, in our certain data, it's quite common data like sorry.
I mean, one intuition, I guess, is the LLMs may just be confused, right? Getting too much data, get some kind of a cognitive overload.
Yeah, that could be one of the reasons, to be honest. Yes. Yeah.
Is that what you guess?
Most likely that also could be true. And also one of the other thing that I noticed, but I mean, need further examination, of course, is that rather than causal, maybe LLM actually just noticed the correlation on the data. But again, I did not do empirical research on that, but just my impression. Yeah. Okay. I think you asked maybe first.
Yeah, so you said you tried the experiment with different temperatures and then averaged them.
Yep.
So I was curious, was there some performance difference between like temperatures?
Very slightly.
Okay, not really.
Not really, not like very big, just slightly, yeah.
Okay, yeah. Thank you for that. I have maybe a stupid question, but did you try to test your models on random matrices of observational data?
So you mean like instead of using a real observational data, just random numbers? I mean, actually, I wanted to do that, but in the end, actually, I forgot. Sorry, yeah. But yeah, I mean, one of my colleagues, when I'm presenting this, he also suggested that, but I did not have time or I was forget. But yeah, you asked that. now it reminds me of that, but for so far not yet.
Yeah.
But I'm thinking of it.
Because, if
Mhm.
it doesn't change anything, it means that everything is related to the level of the variables. Or...
Yep.
Yep.
Could be only dependent on the metadata and does not look at the observational data at all, right? Well, that of course one possibility, but at least in our finding, we get an improvement when we add the observational data here. So but definitely it does have a meaning, but whether if we change this into completely random, it will also improve maybe, but that's I cannot say. But at least when adding it, it does improve compared to without any this data. Yeah.
That's a great question.
Yeah.
Like, what if you give like a wrong observation data?
Sorry?
What if you give a wrong observation rather than
Yeah, that is why. I
random,
mean,
or
Mhm.
you give a Pearson correlation matrix, but
Mhm.
it's not the correct one.
yeah,
You
that's
change the direction
mhm,
of
yeah.
your positive and negative.
Yep, I should really do that.
It would be interesting to see.
Yeah.
Response.
Sorry.
Sorry.
I don't remember the order of the question, so
Okay, please, would you mind to go to slide number 3?
3.
Yeah.
Okay.
Here,
Mhm.
I was wondering, on the middle of it, you established the causal graph.
Yeah, okay.
Could you please elaborate a little bit more? Why would I need to go in the knowledge graph?
So
Once-
knowledge graph, sorry.
Yeah, because after causal graph,
Okay.
there is the knowledge graph. Am I understanding correctly?
No, actually there is no knowledge graph here. So on the
Knowledge base, sorry.
oh,
Knowledge base, so sorry, I made a mistake. Knowledge base.
Okay.
So why do I need to go in the knowledge base?
Okay.
If I have already established,
the causal graph.
yes,
Yeah. So in this certain illustration is for this, basically the causal graph resulted from this statistical based causal discovery is we don't know whether it is correct or not, right? Because I mean, most of the time we don't have the ground truth. So what we want to show here is that the knowledge-based causal discovery could help in verifying those causal graph. So whether
why don't apply, if I have to use the
Mhm.
knowledge base, I go straight away and without building the causal graph, because that is your ground truth, if I understand correctly. So you are kind of verifying if the causal graph is complied with the knowledge base.
actually that's not what it really means
Okay.
in the certain illustration. We just want to show that the output of the statistical based causal discovery is a causal graph. Basically, what is the whether there is a causality between certain variables in our observational data. However, normally this causal graph is verified by human expert, as far as I know.
Yeah.
And here, this knowledge-based causal discovery is trying to help or replace this human expert in checking whether the causal graph is actually correct or not. Yeah, so basically using LLM to verify this is just one use case of knowledge-based causal discovery, not exactly this
So
research.
Yeah, just a compliment. So we are
Yeah.
considering causal relationship between two variables.
Yes,
And
MOOC and
that's,
cancer.
that's it, basically.
Yeah.
We're not talking about more complex graph structures, actually. So this is just an illustration.
Yeah, this is
You could build up a causal graph based on several of such observations or such
Mhm.
causal relationships.
Yeah.
If you want to make it more complicated, but it's actually not part of the study.
yes, exactly. So this is basically just a little bit related works, what is called on this knowledge-based causal discovery. And one use case of this knowledge-based causal discovery is to verify the causal graph from the statistical based method.
So is the motivation for what comes later then?
Kind of, yes. Sorry if it is confusing. It's
Okay,
not really related to the current.
The motivation,
yeah.
okay.
Yep,
now
yep,
it's clear.
exactly. It's just to show what is happening in this causal discovery research in the era of
Now
LLMs.
it's
Yes.
Classical
Yes,
approach.
yes.
Okay.
So it is called knowledge-based causal discovery, but this knowledge is not knowledge graph, but more to this LLM base.
Yeah.
That
So
uses
basically
knowledge.
The knowledge base is domain expert.
Exactly,
So after
exactly.
you get the causal, you put the domain expert to verify.
Normally, yes.
Yes, but you are
But yeah,
picking him off and put the LLM.
exactly, the current trend is
Okay, now,
people
so,
start,
thank you.
yeah, people start to use LLM to replace the expert kind of.
Yes, okay, thank you.
Yep. Okay.
Where during the basically the answer from the large language model.
I'm sorry.
Sorry, where all the answers
The
from
answers.
the answer from the large language model taken with a truth degree of 1, or was also some kind of confidence value from log probabilities constantly?
Oh, here we don't look at the probability. We just like, so for example, in the pairwise prompting, we constrain the output to basically choose in one of the option, and at least I did not look at the probability of the LLM, the confidence of answering those. Yeah, but that could be, could be interesting to look at whether LLM, how confident LLM in answering of each of. Yeah, we could look at the logit and yep, that's additional analysis, I guess. Yep, thank you.
Okay. Thank you, everyone. And thank you, Yuni. That was a great talk.
Thank you.
If you have any questions for us,